Good morning. I hope that you are all doing well, you're healthy, and you're happy. I'm excited about our lesson today. I'm glad that you tuned in. You tuned in to Math 8, so we are going to be looking at our third essential concept today. Our third essential concept is on scatter plots. Scatter plots, slope, and Y-intercept. And here's what it says that the student will be able to do. The students will be able to construct a scatter plot that compares two sets of data to determine the two sets have a positive, a negative, or no association. You will also be able to find linear models of the form y equals mx plus b, which we will look at that slope-intercept form, to solve problems by interpreting the meaning of the slope and of the y-intercept. So you guys ready for that? All right, let's go. So what is a scatter plot? First, we need to define what a scatter plot is. A scatter plot is a graph. It shows the relationship between bivariate data, and it's graphed as ordered pairs on a coordinate plane. If you look right here, I have a coordinate plane kind of sketched out for you. It would be comparing two things here. We could be comparing temperature and time. We could be comparing money and time. So we're going to look at some examples where we're comparing two things. And that's just what bivariate data stands for. Bi meaning two variables, two things, and we're going to see what their correlation is, how they are associated, okay? So let's talk about association. I know that I'm in two associations. I know that I'm in Mobile Educators Association as well as Alabama Educators Association. What that means is I'm in a group of educators for Mobile and for Alabama. Maybe you are in an association. Maybe you're in an athletic association. Maybe you're in some type of program where you are grouped with someone. It's how you relate. So if you were talking about the association with educators, we all relate to education. If you're talking about athletic association, we all relate to something with athletics. So we're going to look at some associations, though, that are with scatter plots. There are different types of trends that we look at when we're comparing two variables. We have a positive association, and when we're looking at associations, we look at them from the left to the right, just like you read a book. You read a graph from left to right. So we will look at it, and as we see the positive here, it starts down and it goes up, which is what we call an incline. It increases from left to right. So that would be a positive association. Where the negative association from left to right, it decreases, it declines. And then we have no association, it's just everywhere. And it kind of acts as the scatter plot. When you hear the word scatter, you're probably thinking everywhere, right? So the no association is, it doesn't increase, it doesn't decrease, it's just everywhere. And so we also have strong and weak. If you look at strong positive association, that means it's very tight. It's very close to a line. But the weak positive association, it's still increasing, but it's a little more relaxed. It's a little more spread out. But you can still see a trend of a positive or an incline. No association, scattered everywhere. And then we have weak and strong negative. So the weak is, it's still declining as we go from left to right, but again, it's kind of relaxed. And then the strong negative is very tight, it's close together, and it's declining. So let's look at this example. The scatter plot below shows the average traffic volume. Well, we were talking about volume last week, right? But this is talking about traffic volume. So how many cars are on a freeway? And the average vehicle speed, so how fast the cars are going. On a certain freeway for 50 days in 1999. So they gave us a graph here. We have our average vehicle speed is on our y-axis, on our vertical axis. And then we have our average traffic volume, which is on our horizontal axis, which we call x, okay? So as we need to determine what this problem is, it's asking us which statement best describes the relationship between the average traffic volume and the average vehicle speed shown on the scatter plot. So before we go, we need to kind of make sense of what it's asking. We can kind of think about how this would play out. What is the typical situation here? As traffic is increasing, as the volume of traffic increases, I'm thinking of like maybe Atlanta or maybe even Airport Boulevard here in Mobile, or Schillinger's Road. I know I've gone out over the weekend. There was a lot of traffic. So as traffic volume increases, what can you expect the speed to do? That's right, you're going to have to slow down because more people are on the road. There's more people that are stuck at traffic lights, or there's more people that are traveling. So more people means the speed is probably going to decrease. When you're out on a freeway and there's no one, you can determine your speed. Whether that would be a lot different than if there were 100 people out there in the same area. So if we look at our graph, you can tell which association we have. So looking at our positive, our negative, our no association, what is our graph doing? It's declining from left to right. So this is actually negative association. So we need to make a decision here. Is it A, as traffic volume increases, the vehicle speed increases. So that would mean this is going up as well as this is going up. And that would have a positive association. That's not what we have though. We have a negative association. Let's look at B. As traffic volume increases, vehicle speed decreases. So as traffic is increasing, numbers are going up, there's more people on the road, vehicle speed decreases. So if you chose B, that was correct. As traffic volume increases, vehicle speed has to decrease because more people on the road, you got to slow down a little more. And we know that this wouldn't be true because both of these say they first increase and they decrease, or they first decrease and they increase, and that would look like a kind of like a heart monitor. It would be going up and down. Okay, good job, B on that one. All right, let's look at Miss Moore. It said that Miss Moore recorded the age and the shoe size of each student in her physical education class. Then she graphed the data below. Okay, so we have ages of people in her class, 11 years old, 12, 13, and 14. And then what shoe size they wear, okay? If we're thinking about association, what type of and that's what our question asks us, which of the following statements about the graph is true? They want to know about correlation or association. Correlation is just the mathematical term for association. It's a little more educated, I guess, or not necessarily educated, but it's just a little more technical. Correlation is a little more technical than association. So we want to see what type of correlation that this graph would have. Well, thinking in your head, using logic. A lot of times when we're looking at things like this, we're using our logic, we're using our thinking skills so we can determine if I was 11 years old, could I wear a size 6? Could I wear a size 9? Could I wear a size 8.5? Absolutely. So really your age, even though you can narrow it down to a certain size, because obviously I probably wouldn't wear the same size as a baby as an 11-year-old, but I'm probably in a particular range. But just because I'm 11 doesn't mean I have to wear a 6. Just because I'm an 11 doesn't mean I have to wear a 9. In fact, you and your friend may both be the same age and wear different size shoes. So that's why this graph shows no correlation, which would be answer choice D. So if you chose answer choice D, that is correct because you can tell our graph is all scattered. Age does not determine the shoe size. The shoe size does not determine the age. Now you're going to see that maybe, yeah, they do fall between 6 and 9, but again, they're scattered out. So good job there. Let's look at this one. Mr. Thomas wanted to know if the amount of class time that he gave students to study affected their test scores. And looking at the scatter plot below, it says what kind of relationship between the class study time and the test scores is shown on the scatter plot. So again, we're looking for association, looking for correlation, and that was in our essential concept. We needed to determine negative, positive, or no correlation. So what do you think you see here? Is our graph showing an increase over the time, the study time? The test scores are increasing. Is our graph showing that over the study time our scores are decreasing? Or is there no correlation between our study time and our test scores? All right, that's right. If you chose positive, which would be B, positive association, the more time that you study, the higher that your grade will be. You see that at 5, we'll say those are minutes, even though it doesn't tell us they're minutes. We're going to say probably 5 minutes. At 5 minutes, some students scored around a 72 and a 75. But at 30 minutes, the student scored around an 87 or an 88, almost a 90. So, we can predict that maybe if you study for 45 minutes, you might make an A, or 45 minutes to an hour. So we can look at graphs and determine by the trend, determine by the association, what would happen here. So we have a positive association or correlation. More study time, higher grades. Hopefully you are studying over this fourth quarter. We're almost finished. So line of best fit. Oftentimes when we have scatter plots, we draw a line of best fit to understand our data, to understand our slope, to understand our Y-intercept, and to interpret. So we have crickets that are chirping and the temperature. In the summer months, when the temperature rises, those crickets get to chirping. So we can see here that the number of chirps, more chirps, as the temperature rises. So you would sketch a line going through the middle of your data. When you want a line of best fit, you want most of your data to be surrounded by this line. And if some of it touches it, that's great. That's what you want. You want it to go through the middle. And approximately the same amount of data that's above the line, you also want it to be below the line. That would make it in the center. So this is the line of best fit for this data here, and we can show that it's a positive association. It's increasing. So we know that we can interpret this by saying that the number of chirps increase as the temperature increases, because it's positive, okay? So a 5th grade class conducted a 5-minute experiment that involved heating water, heating time and water temperature. So they were boiling something. And so the result of the experiment is represented in the graph below. So over 5 minutes there's our time, our two data, bivariate data here, time and temperature. So over time, what was happening to the temperature of our water? And if you've ever boiled water, maybe you've cooked a hot dog or you've cooked some macaroni and cheese and you've had to boil water. You know that over time, that temperature starts to rise and boil in that pot. So over time, we know the temperature will rise, and this will be a positive correlation. So let's look at some of our answer choices to see. It says, what prediction can be made based on the information gathered? The water temperature remains the same as the heating time continues? No. If you have the temperature turned up over time, it's going to increase, right? The water temperature decreases as the heating time continues? No. A pattern cannot be determined. We see that on our graph. It's not scattered. Or the water temperature increases as the heating time continues. The more time you spend heating it, the hotter it's going to get. So that would be answer choice D. Hopefully that's the one that you selected as well. You guys are doing great. All right, so now we want to talk about slope and Y-intercept. The slope and Y-intercept, well, you're going to use this form. My kids just say y equals mx plus b. It could also be negative mx minus b. So that's just the generic form, is that the slope comes before the x and then the Y-intercept is after. And so we need to determine, you've probably already studied some slope and Y-intercept if you've graphed this quarter, but we need to determine review what the slope is. So slope is the vertical change over the horizontal change, and I put that right here. In middle school, we kind of talk about it in this formula, y2 minus y1 over x2 minus x1. But when you get into high school, they may talk to you about delta y over delta x, which is the change in y over the change in x. So it's the change in the vertical over the change in the horizontal. And just like the word slope, you kind of have heard that word probably before if you've ever gone skiing, if you've ever used a bike, or you've been on what are the roller blades or the scooters. The slope of a hill. What is the slope of the hill? And so you want to know how high it is, how steep it is. And that's the changing rate. And then the y-intercept is where the line intersects the y-axis. It's the initial value, or the flat rate sometimes we call it, because it's where we start, our starting point, and then what is it increasing to, or what is it decreasing to. That's how we look at a graph and determine that. So we're going to look at some equations just to identify the slope, and in a minute we're going to actually pull out the slope on a graph. So if I just identify it using my slope-intercept form, that's what we want to focus on. My slope is always the coefficient of the x. Remember, coefficient is the number in front of the x. So my coefficient here for number 1 would be 3. But remember that our slope is in a fraction format. It's in a fraction format, so we know if it's a whole number, then the slope, it needs to go over what number? And a lot of kids get confused with this. They think it's 0, but it actually needs to go over 1, because that's what holds its value. If I have 3 over 1, it's still 3. If I have 3 over 0, it's undefined. We can't have 0 in the denominator. So 3 over 1 would be my slope here, and my y-intercept would be 5. Good. What would my slope be on the second one? I have a negative now. If you said negative 4 over 1, that is correct, because it's still negative 4 has to be in a fraction form, so negative 4 over 1. And my intercept, you have to include that sign there. My y-intercept would be negative 2. What about number 3? We can clearly see our slope there. It's our coefficient in front of x. What is our coefficient in front of x on number 3? 1/2, and it's already in fraction form. So the vertical change would be 1, the horizontal change would be 2. So that's already in slope form. We don't need to put a 1 under that. That's 1/2. But what is our intercept? There's nothing there. So what number would make nothing? 0. So our y-intercept here is 0. And sometimes you might see them say plus 0, but a lot of times they're just not going to put it there. But you have to know that if it disappears, it's 0. Let's look at number 4. What would make our x term disappear? What number multiplied by x would make it completely disappear? 0. So our slope on number 4 is 0, and our y-intercept is 6. It's still there. So when the x term disappears, the slope is 0. When the b term disappears here after the x, the intercept is 0. And last one, we don't have a coefficient in front of x, so what do we know is understood to be there? When we have a variable by itself, it's understood to be a 1 in front of it. So our slope on number 5 would be 1 over 1. And our intercept on number 5 would be 2. Very good. So it says determine the slope and y-intercept of this line. So we have a line here, and what is it doing? Is it increasing, decreasing, or is it scattered? Well, it's not scattered because it's a line. But from left to right, I tell my students this. If you've ever played Chutes and Ladders, it's a little board game. From left to right, when you hit the line, are you sliding down? Or when you hit the line, are you climbing up? So from left to right, as I hit this blue block here, I'm sliding down. So this shows me that this is a negative slope because it's going down, it's declining. So now I want to find the exact slope, how much it's declining, the rate at which it's declining, and I also want to find the y-intercept. Typically, the Y-intercept is the easier one when you have a visual here, because you can just see where does this line hit the y-axis. And you can see that the line hits the y-axis right here at -1. And when you have the y-intercept, x is always going to equal 0. And we have that here in our ordered pair, that x is 0 and y is -1. But anytime you're on this y-axis, you're not going left or right, your x is going to equal 0. Okay? Let's see how our line is declining though. Let's see our slope. So our change in our y would be 1, 2, 3, 4. So we're declining 4 and over, remember we did this with Pythagorean theorem, 1, 2, 3. So our change, our slope would be -4 over 3. And so I could predict my next dot here, my next point. I could go down 1, 2, 3, 4, and 1, 2, 3. That's where my line's going to continue to go. I could also go up and left, and it would give me my same slope. It ends up looking like a staircase. A lot of times my students say it's either a downward staircase or it's an upward staircase. In this example, it's a downward staircase. We'll be going down. We have one example where we need to use the y-intercept to find out our, let's see, researchers gathered data to predict the number of new plants, new type of plants, in a state park after a certain amount of years. So again, we're comparing two things. We have years, we have the types of plants. And so the scatter plot data, she determined the equation of the line of best fit. So this is our line of best fit. And they want to see, based off this equation, what is the number of new types of plants there will be after 24 years. So we had a scatter plot. We found the line of best fit. This is it. And now we want to plug in our x value, because it said that's what years is, x, into our formula so that we can determine which one is correct. So we have 0.25, that's our slope. We want to write that as a fraction. What do we know 0.25 is as a fraction? That's right, 1/4, a quarter. So we have 1/4 here times x, which we know is 24. So 1/4 times 24, which is just 24 over 4. 6. So we have 6 plus 8. 6 plus 8 is 14, which is B. Good job. So we're going to wrap it up here. Today we learned how to interpret a scatter plot. We determined its association, whether it was a positive, negative, or no association. We talked about how to sketch a line of best fit through our data and how to find the slope and the y-intercept given a line and an equation. Remember, the slope is the m before the x, the coefficient, and the y-intercept is after. We note it as b. Next week, I know you were thinking maybe this was the last week because you're finishing up this week with your online and your packets, but next week we're going to put all of them together and we're going to review all 3 essential concepts. Pythagorean theorem, which we did first, volume of a cylinder, cone, and sphere, which we did these last couple of weeks, and then scatter plot, slope, and y-intercept. And we're also going to give you a preview of 9th grade. So you'll want to see next week so you can see what you're going to be doing once summer's over. So tune in with us next week. I hope that you finish your packets, finish your online courses, and then you can enjoy summer. Thanks for tuning in. See you later.